Section 2.4, Graphing a Function Rule. Now it sounds odd calling it a function rule, but basically it's the same thing as graphing an equation. So that's what you're going to be doing. If you look at on page 117, we're going to skip the solve it today, but we can look at the shaded box in the middle of the page where it says essential understanding. The set of all solutions of an equation forms the equation's graph. Now today, we're going to be graphing lines, so the graph is going to be in the form of a line. It's important to understand that when you graph a line, that represents all of the solutions. So this is a perfect definition that you need to memorize. The set of all solutions of an equation forms the equation's graph. So when you connect all these dots together and you make a line, all of those points on that line represent solutions. A graph may include solutions that do not appear in the table. A real-world graph should only show points that make sense in the given situation. That's an important idea that we're going to hit on in a little bit. When you graph something, you have to make sure that the line you are graphing actually represents the situation that you're talking about. So we're going to start with the got it problem at the bottom of page 117. Y equals 1/2 x minus 1. In the course of these next few chapters, I am going to be reviewing with you and showing you that there are many ways to graph something. Many. You can use slope-intercept form. You can use x and y intercepts. You can also use a t-table, which is what we're going to be using today. This is probably review for you, since most of you probably have done this before. A t-table is just what it sounds like. A table in the shape of a t. All I want are 3 values. You can pick however many values you want, but you got to have at least 3. Pick any value you want to plug in for x. Remember, that's your input. Your input is x. Your output is y. So here, you can actually plug in 0, 1, and 2, which most of the time, that's what I would suggest. You could plug in 100. It's up to you. But remember, you have to graph it. So right here, I'm going to plug in values of x. Since I have to take that value and times it by a half, I only want to pick numbers that I actually can take the half of to give me a whole number. So I would only pick multiples of 2, like 2, 4, 6, and so on. So you want to graph this. So we're going to graph. I'm going to pick, for my values of x, 0, 2, and 4. Once again, you can pick whatever values you want. Now, I'm going to show this once because for the most part, being advanced students, I would expect you to be able to do most of this in your head. When you plug in 0, you're going to plug in 0. You're going to plug in 2. And you're going to plug in 4. So if you plug in 0, a half times 0 is 0, minus 1, that's going to give us a negative 1. Plug in 2, a half of 2 is 1, 1 minus 1 is 0. Plug in 4, a half of 4 is 2, 2 minus 1 is 1. So now all we do is we graph our equation. Now when you graph, you will notice here that I am going to be graphing more than just my first quadrant because I have a negative value. So one thing to note when you draw your graphs, make sure your axes have arrows at the end. Also make sure that you label them x and y. So now let's graph our line. 0, negative 1, 2, 0, and 4, 1. When you graph, please make sure you use a straight edge, a ruler, or something that's going to give you a nice straight line. I don't want something that's going to be curvy and it's not going to look like it goes through the 3 points. So we connect our dots. Make sure when we connect our dots, we're not just stopping at our dots. We're not drawing a segment. You are drawing a line that goes all the way through our dots, and you're going to put arrows at the end. Please make note that there are an infinite number of solutions here that make this equation true. All we did was graph 3. That's all I wanted you to use is 3. But there are millions and millions of points on this line that actually make the equation true. Now turn the page to page 118 and we are going to do practice A problem number 1. Same type of thing. Let's make a t-table. I'm going to pick 0 because to me that's the easiest. And because we are dividing by 4, this is 3/4, We're dividing by 4. I'm going to pick multiples of 4. Once again, you are more than welcome to change 3/4 to 0.75 and times by any number you want. You can plug in any number you want for x. So I'm going to plug in 0. 3/4 times 0 is 0 plus 2 gives me 2. If I plug in 4, 3/4 times 4, well, if you don't remember, 4 times 3 is 12, divided by 4 is 3, so 3 plus 2 is 5. I plug in 8. A fourth of 8 is 2. 2 times 3 is 6, plus 2 is 8. Now, if you don't know how I got that, you can take 8 times the numerator. 8 times 3 is 24. 24 divided by the denominator is 6, plus 2 is 8. So now let's graph this. I'm going to graph 0, 2, 4, 5, and 8, 8. I'm out of room here, so I'm going to connect the dots. Now once again, I could have counted by 2's, I could have counted by 4's on my x-axis. But there's your line. So now let's look at the got it problem A under problem 2. The function rule, now once again, the function rule is just a fancy name for an equation. The equation W equals 8g plus 700 represents the total weight W in pounds of a spa that contains g gallons of water. What is the reasonable graph of a function rule given the capacity of the spa is 250 gallons? Now before you begin, look at the shaded region above that. When you graph a real-world function rule, choose appropriate intervals for the units on the axes. Every interval on the axis should represent the same change in value. If all the data are non-negative, show only the first quadrant. We've kind of already talked about this before, but there's no need to draw more of the graph than you actually need. Alright, so we're just going to graph this. W equals 8g plus 700. Now if we make our t-table here, remember this is x and y, but we're not talking about x and y, we have two other letters. G would be the number of gallons we pick, and W represents the total weight. So we're going to start with 0, because that's the least amount of water we could fill. So if we plug in 0, that would give us 8 times 0, which would be 700. Now, you could plug in 1 and get 708. Then you plug in 2 and get 716. But here's what's different about this problem. We know that the capacity of the spa is 250 gallons. So we have to graph up to 250 gallons. Then we stop, because that's the most amount of gallons of water we can plug in. So I want the last value to pick is 250. So if you would calculate 250 times 8, well, 250 times 8 is 2,000. 2,000 plus 700 would be 2,700. Now I'm just going to pick one in the middle. I'm just going to pick 100. 100 times 8 is 800. 800 plus 700 is 1,500. Now once again, you can pick any values you want. You could pick 50s. You could pick 150. You could pick 4. It's up to you. But now we're going to graph this. We only need the first quadrant since we're talking about number of gallons of water and weight, and you can't have a negative value of either of those. Your x-axis is actually gallons of water. We have to make sure we label. And our vertical axis is the total weight, which we know is in pounds. Since I have to go on the g-axis, which is like your x, I have to go from 0 to 250. I'm going to count by 50s. So 0, 50, 100, 150, 200, 250. Now once again, it's going to look much nicer on graph paper. And then I have to go up to 2,700. So I'm going to count by thousands. 1,000, 2,000, 3,000. Once again, you do not have to count the same for your x-axis that you do for the y. All right, so 0, 700, 100, 1500, and 250, 2700. Now, if you graph this correctly, you would have a straight line. Now, notice something I did. I actually did this wrong. What's wrong with this? It shouldn't be a line. This is not a line. First off, and this is why you need to make sure your reasonableness of your graph makes sense. The lowest value of gallons of water you can plug in to this equation would be 0. So this is not a line that goes past the 0 to the left side of this point. At the same time, the maximum capacity of the spa is 250 gallons. So the maximum value of G that you can plug in is 250. Therefore, your arrow will not continue past this point. So really all we're graphing is a segment between 0 and 250, which is going to lead into a lot more interpretations later on about being continuous or not. But this line would be continuous. I would connect it. You will learn later that not everything is connected. For example, as you add water, you're not going to jump from 1 gallon to the next. You're just going to pour it in. That's why we connect all these dots. So now let's look at B. What is the weight of the spa when it is empty? Well, if it's empty, how many gallons of water is in it? 0. And what is the weight when it's at 0? It's at 700. So answer B would be, the weight would be 700 pounds. On the bottom of page 19, you will see the key concept: a continuous graph and a discrete graph. A continuous graph is a graph that is going to be unbroken. It's basically a solid line or a segment that connects everything between the points. A discrete graph is composed of distinct, isolated points. Now, to give you an example of how that's going to work, imagine that you are putting money every month into a savings account for college. Every month you put a certain amount in. So the first month, let's say you're putting $50 every month. The first month you put $50 in. The second month it jumps to $100. So you're not going to connect the dots there because you don't have an amount between 50 and 100 that's going to the bank, so it jumps. But let's say you're talking about snowfall and there's 12 inches of snow on the ground. If it starts melting, it doesn't jump from how many inches is left to another amount of inches. It continuously melts. Therefore, if you had a graph representing melting snowfall, you would connect your dots. So turn the page to page 120 and the problem 3. Now, as you can see, I already did the problem A for you and have the answer. So if we quickly look over it, it says the amount of water W in a wading pool in gallons depends on the amount of time, T in minutes, the wading pool has been filling, as related by the function rule W equals 3T. It's an easy equation to graph. I have a T table here already written. And you have your labels, etc. It's an easy graph to draw. The only thing I want you to look at is, notice I have my dots. I do not have an arrow down here because it starts at 0. Because you are filling a pool up with water, it doesn't jump between points. It continuously increases above the amount of water that's in the pool. Therefore, I connect my dots to make a continuous line. Now, if you look at B I'm not going to do, but let's just quickly talk about it. The cost C for baseball tickets in dollars depends on the number N of tickets you buy, as related by the function rule C equals 16 times N. Basically, every single ticket you buy is $16. The cost is what you'd have. So if you graph this, you graph 0 tickets would be $0, 1 ticket is 16, 2 tickets is 32, and so on. Would you connect those dots? No, because if you buy 1 ticket, it's $16. If you buy 2 tickets, it's 32. It's not going to cost anything between that. So therefore, you're not going to connect your dots. It's going to be a discrete graph. Now turn to page 121 and look at the box in the middle of the page. The function rules, once again, I'm just going to say the equation. The equations graphed in problems 1 through 3 represent linear functions. That means they make a line. You can also graph a nonlinear function, basically something that's not going to make a line. When a function rule does not represent a real-world situation, graph it as a continuous function. So whenever you have something that you're graphing that has no context in a word problem, you just connect the dots, make it a line, or connect it to make a continuous function. So we're going to do the got it, number 6, and number 7. So the got it. I'm going to make my t-table, and I'm just going to plug in 0, 1, and 2. If I plug in 0 to the third power, that's 0 plus 1, which gives me 1. I plug in 1. 1 to the third power is 1, plus 1 is 2. 2 to the third power is 8. 8 plus 1 is 9. Now, this is something that's going to be different. Whenever you have an exponent, x squared, x to the third, x to the fourth, I want you to plug in more than 3 values. And more importantly, let's plug in some negatives here. I'm going to plug in -1 and -2. Now, if we take -1 to the third power, that's going to give me -1 plus 1, which gives me 0. Now I'm going to plug in -2. -2 to the third power plus 1. -2 to the third power gives me -8 plus 1, which gives me -7. So when I graph this, you're going to notice that you're not going to get a line at all. If I plug in 0, 1, so I plugged in 0, 1, so I'm going to graph 0, 1, 1, 2, 2, 9, -1, 0, and -2, -7, which is going to be down here. Now you're going to look at this and go, what in the world is this kind of graph? You will get much more used to graphing these kind of graphs that aren't going to make lines. So we're going to connect the dots. They're going to be curving. So it's going to look something like this. We put arrows at the end. That's a very rough drawing, but that's what it's going to look like. It's going to go up and then kind of taper off and then go back up again. Now let's do practice problem 6. Now, if you like to show your work for these, because these you should be able to do in your head. However, if you want to make an extended t-table to show some work, you're more than welcome to. So I'm going to plug in -2, -1, 0, 1, and 2. Here's the rule that I always would have when you have exponents or you don't have linear functions. I always plug in 5. So if we plug this in, this is going to be negative times -2 to the third power. Please note that these negatives do not cancel. They do not cancel. They do not cancel. So I do -2 to the third power. That's -8. -8 times the negative gives me +8. I plug in -1 to the third power. -1 to the third power is -1 times a negative is +1. I plug in 0. It's just going to give me 0. I plug in +1. That's going to give me 1 to the third power, which is 1 times negative, which is -1. I plug in 2, and I'm going to get -8. So if I graph these, -2, 8, -1, 1, 0, 0, 1, -1, 2, -8, your graph is going to look something like this. We put arrows at the end, and you have a nonlinear function. Number 7 is an absolute value graph. Absolute value graphs, by the way, here's a little hint. Absolute value graphs are always going to look like V's. Either V's that are facing upward or V's facing downward. They will come to a point. So if we graph this, I'm just going to pick, 5 values, 0, 1, 2, 3, and 4. If you plug in 0, 0 minus 3 is -3. The absolute value of -3 is +3, minus 1 is +2. I plug in 1. 1 minus 3 is negative 2. The absolute value of negative 2 is positive 2. Minus 1 is 1. You should notice a pattern here. 2 minus 3 is negative 1. The absolute value of negative 1 is positive 1. Minus 1 is 0. But something's going to happen here. 3 minus 3 is 0. 0 minus 1 is negative 1. And then number 4. Plug in 4. 4 minus 3 is 1. The absolute value of 1 is still 1. Minus 1 is 0. Notice what's happening. Let's just plug in one more to see what would happen. 5 minus 3 is 2. The absolute value of 2 is 2. Minus 1 gives you 2. Now it should be fairly easy. You guys should have no problem plugging in these x values into a simple equation. But notice what here is happening to your graph. Let's graph it. So I'm going to graph 0, 2, 1, 1, 2, 0, 3, negative 1. It looks like a line, but then 4, 0, 5, 2. Absolute value graphs will always look like a V. And there is your answer. So the key concepts today, you have 3 of them. Key concept 1 is when you have a linear function, just plug in values, any values you want for x, plug it in, and connect your line. That also includes real-world problems, determine if it's going to be discrete or continuous, and then see what's going to happen when you graph nonlinear functions.